Hello everyone. Okay, in this video is the demonstration of the shear stress calculation in the beam. Okay, so let's look at this problem. Okay, this example is from 12.1 from the textbook. He said there's a beam, but this beam is made up of two parts. Okay, this beam is made of two boards. Okay, and the boards, the cross section of this beam is like this. One is horizontal, the other is vertical. So it's just these two board and hold together. Use a glue to hold together. Okay, it's two boards. Use a glue hold together. And he said determine the maximum shear stress in the glue to hold these two board. Okay, so that just means he put some glue on this surface and then attached to on the other board. Okay, he said determine the maximum stress this glue has to provide to prevent the shear of these two boards. Okay, so actually this problem. Okay, so let's look at the formula for the calculated shear stress in beam. Okay, for the shear stress in beam, okay, the formula is tau is equal to VQ over IT. Okay, so if you want to determine the maximum shear stress in a group, okay, so actually you need to know what's the maximum shear stress on this beam. Okay, and the maximum shear stress on this beam, yeah, this picture, okay, you have to use this picture to determine the maximum shear stress applied on this beam. So this is a two support, this is a roller support, this is a roller support, and this is the smooth support. I think it's a smooth support. I forgot. Okay, this is small support, this is roller support. Okay, and this distributing load here, and then you have to use this information to determine the maximum shear stress applied on this beam. Yeah, but this problem that will make this problem calculation process too long. Okay, so I just tell you, okay, the maximum shear stress in the beam is 19.5 kilonewton. Okay, so just tell you that this V is 19.5 kilonewtons. Okay, we'll talk about similar problem later. Okay, so in this problem you have to draw a so-called shear moment diagram. After you draw the shear moment diagram, you will understand why the maximum shear stress is 19.5 under this distributing load and this support. But this problem we just calculate the shear stress directly, so I just tell you the shear stress is 19.1 kilonewton. Okay, and the next problem is so the calculation of the shear stress. Well, always we need the thickness and moment of inertia and the Q of this cross section area. Okay, he said want to determine. So I need to draw a big picture. Okay, actually it want you determine the shear stress. Okay, I think I call this point. Okay, then I call this point, I call it B. Okay, the B is just right next to or very close to the dash line, but a little below the dash line. Okay, so because it make a glue on this surface, okay, so actually he want to calculate shear stress just right a little below the dash line. Okay, so B is here. Okay, and okay, so and this is very important because this information can let you know, okay, to help you to calculate the B. The Q. Okay, we'll talk about Q later. Okay, the next thing is the moment of inertia of this cross-section area. Okay, so when it comes to calculate the moment of inertia or the Q, the first problem you have to ask is where is your neutral axis? And in this problem, actually, this problem doesn't tell you any information about neutral axis. Yeah, he drew a neutral axis here, but what's the distance here related to the base? Okay, so that's here is a base. Okay, so where is the neutral axis in y direction? Okay, what's the distance between the neutral axis and the base? You have to calculate it. So how to calculate neutral axis actually is very similar to calculate the centroid of a composite area. Okay, so right now we have a T shape cross section, so we can divide this T shape into the two simple rectangular. And it's two simple rectangular and determine its centroid of each area. So the centroid is here, the centroid is here. Okay, so I call this 1 and I call this 2. Okay, so the first of all, let's calculate the neutral axis. Okay, y bar. What's the y bar? It's equal to a1 plus a2 and a1 y1 plus a2 y2. Okay, so what is a1? A1 is 30. A1 is here is 30 millimeter times 150 millimeter. So it's 30 millimeter times 150 millimeter. Yeah. And so do I have show you the value? Okay, I can show you the value. Okay, so it's just equal to 4500 times 10 to the power minus 6, and it's m squared. Okay, so what is a2? A2, yeah, here is 30 millimeter. Yeah, I think it's the same. 30 millimeter times 150 millimeter. Yeah, it's the same. And that's good. This quality is good. Okay, you don't have to calculate another area, so it's just equal to 4500 times 10 to the power minus 6 m squared. Okay, so what is y1? What is y1? Y1 is here. The centroid of area 1 is here. So what's the y1 here? Y1 is, okay, we said its base is 0. Okay, so what's the y1? So here is 150 millimeter. Here is 30. So I think it's equal to 100 plus 30 over 2 millimeter. I think that's the y1. So it's 165 times 10 to the power minus 3 meter. Okay, so that's the y1. So what's the y2? Y2, I think here is 150 millimeter. Yeah, here 150 meters. So millimeter. So y2 is just 150 millimeter divided by 2. So it's 75 times 10 to the power minus 3 m. Okay. Okay, so we have y1, y2, a1, and a2. So what's the y bar? So you just put everything together. Okay, so a1 plus a2, I think it's 9,000 times 10 to the power minus 6. So a1 4500 times 10 to the power minus 6, and 165 times 10 to the power minus 3, and here the same thing, 4500. And the 75 10 to the power minus 3 up. So we don't have unit here. Okay, actually the number is easy to calculation. So we all divide it by 4500. So this will become 2. So I divide this one. Sorry, this is 6. Okay, sorry, so this divided. Okay, so I think it's very easy. So it's 165 plus, okay, 75 is 240, so it's 120 times 10 to the power minus 3 m. Okay, so actually it's 120 mm. Okay, so we have already determined where is our neutral axis. It's 120 millimeter above the base. Okay, so you have to be careful. So here is 150. So I think it's 75. So here I think probably here is our neutral axis. Probably here is our neutral axis. Okay, this is our neutral axis, and its distance here is 120 millimeter. Okay, so we already find out where the neutral axis is. So after we have the neutral axis, we can calculate the moment of inertia and Q, and to determine the shear stress of the B. Okay, so I need more space, so maybe I have to erase these things out. So if you want to take a note, just please rewind. Okay. Okay, so the next thing I'm going to calculate is the moment of inertia. Yeah, because moment of inertia is, yes, but it's much difficult to calculate. Okay, and then I think we have to use so-called parallel x theorem to calculate the moment of inertia. Okay, so let's calculate the moment of inertia of this cross-section area. Yeah, we have the complicated shape. So we have used the same strategy. Yeah, divided this complicated shape into the area 1 and area 2 and add the moment of inertia of 1 and moment of inertia of area 2 and add them together, we'll get the moment of inertia. Okay, I1 plus I2. Okay, because I1, I2 is much easier to calculate because just a rectangular. Okay, so what's our I1? Okay, I1, let's look at this. Okay, I1, the centroid of area 1 is here. So the neutral axis is not passing through the centroid of area 1. So we have to use the so-called parallel x theorem to calculate the moment of inertia of area 1. But we have to use the formula for the moment of inertia of area 1 circling around its centroidal axis. So it's 1/12 and bh cubic. Oh, what's the result of b? Because right now our neutral axis is horizontal, so the b is the horizontal one. So b is horizontal. What is his distance here? It's 150 millimeters. So it's 150 millimeters is your b, and h cube h is here. Is b is our h. So h is 30 millimeters. So it's 30 millimeter and cubic. Okay, but we have to plus AD squared because the neutral axis is not passing through the centroid of area 1. So we have to add AD squared. So area of this area for area 1 is 30 millimeter times 150 millimeter. And d square, okay, what's d? D is the centroid, the distance between the neutral axis and the centroid. So I think the d is here. Okay, d1 is here. I think this is the d1. Okay, distance between the centroid and the neutral axis. Okay, so here is 120 and the total height of this is total is 150. So here is 30 millimeter. 30 millimeter. Here is 30 millimeter because here is 150. So here neutral axis here is 120. So here is 30 millimeter. And it's 30 millimeters, so we have to add this small distance here. So it is 30 divided by 2. So here is 15. So the d is 45 times 10 to the power minus 3 and the square. Okay, so that's the moment of inertia of area 1. So let's see, it's 45, 30. Yeah, let me see. It's 45. Yeah, it's 45. Yeah, it's 45. Yeah, I have to check my number. I'm sure I will check my number is correct. BH square. Area 1. B 150 millimeter. Oh. Ah, okay. Oh, sorry. That's 2. Okay, sorry. Okay, that's 2. Let's go to BH3 square 30. Okay, so I call it 2 in my notes. Okay. I actually in my notes my 2 is 1. Okay. 2 is 1. In my notes I call area 1 2. So I kind of confused. Okay, sorry. Okay, just give you the answer. Okay, so it's 9.45 times the 10 to the power minus 6. Okay, that's the moment of inertia of area 1. So what's the moment of inertia area 2? Area 2 is here. Yeah, once again, the neutral axis is not passing through the centroid of area 2. So we have to use a parallel x theorem. Okay, but at the beginning, we have to use the formula to calculate the moment of inertia area 2 rotating around its centroidal axis. So it's 1/12 bh3 squared because right now the neutral axis is horizontal. So here is your b, and here is your h. Okay, so maybe I erase this out. Okay, right now here is our h. So b is 30 millimeter, and the edge is 150 millimeter and cubic, and plus AD squared. A is the same, so it's 30 times 10 to the power minus 3, 150 times 10 to the power minus 3, and the D squared. D is the distance between the centroid of area 2 to the neutral axis. So here will be our D2. Okay, so what's the D2? Okay, be careful. So here is 120 and here is 75 because it is a centroid. So here must be 75. Here must be 75. And here is 120. So 120 minus 75, 10 times 10 to the power minus 3, and square, AD square. So what's the value here? So use your calculator. I don't want to show the detail again. Okay, so it's 1.755 times to 10 to the power minus 5. So it's units and to the cube, powerful. So what's our moment of inertia of this cross-section area? So you have to add these two together. You add these two together, it's about 2.7 times 10 to the power minus 5 and 4. So be careful. So add these two together. So we solve the I out. Okay, so next thing is Q. Okay, what is Q? Okay, Q is dependent to your which point you are interested in. We are very interested. Right now we are interested in the position B. So Q is dependent on the position of you are interested. So okay, so do I have to okay, I just keep this here. So okay, so what's our Q? Q is just your area. So right now we're interested in B. So QB. So it's just area times the distance between times so you have to determine which area you are going to calculate. So the actually is A times the Y area times the Y bar. The Y bar is your area, centroid of your area, distance between the centroid of your area and the neutral axis. Okay, so right, which area we are interested in? Because we are interested in B. B is above neutral axis. So calculate everything above B. Okay, B is above neutral axis. So calculate everything above the B. Okay, so you have to calculate here. You are interested in here. Yeah, because in previously we have a slide. Okay, maybe we have the slide show the B. Okay. If we are interested in this point is above neutral axis, so calculate everything above this point. Okay. If your point of interest is here, this point is below neutral axis, so calculate everything below the axis. Sorry, calculate everything below this point. If your point is above neutral axis, so calculate everything above the axis for the Q. If your point of interest is below the neutral axis, so calculate everything below this point for the Q. Okay, so the relative position between the point of your interest and the neutral axis is very important. Point is above neutral axis, calculate everything above this point. If this point is below neutral axis, calculate everything below everything below this point for the Q. Okay, so right now, of this problem, right now, point of interest is B is here, very close to the dashed line, but just a little lower than the dashed line. This point is above neutral axis, so calculate everything above the neutral axis. So we're interested here. So what's the area here? So actually, A is just here. Okay, A is the 30 times 10 to the power minus 3, 30 millimeter times 150 millimeter. That's our A. So what's the Y bar? Y bar is the centroid of this area. Centroid of this area. Distance between the centroid of this area and to the neutral axis. Okay, so what's the distance? here is 15, right? Here is 30. So actually it's 15 plus 30, so it's 45 millimeter, right? Okay, so because B is very close to this dashed line, so we only have to calculate this area. Okay, maybe it is because you mentioned earlier it's a very tiny area here, but because B is very close to the dashed line, so we only consider the area here. Okay. But in the next example, you have to more problem on calculating B. So you will see in next problem. The next problem is more difficult to calculate B. Okay, because in next problem, even Q you also have divided into a simple area. Right now, we only consider area 1 because B is very close to the dashed line, so we only have to consider area here. Okay, so the y is a 15 plus the 30, the distance between the centroid and the neutral axis. Okay, so what's the value here? So using your calculator, I'm not going to show the very detail. Okay, I just want to check my number is right. Okay, this is right, this is right, this is right. Okay, so our Q is 2.025 10 times 10 to the power minus 4 units n to the power 3. Okay, so we have finished calculating the Q. So how to calculate B? So B, okay, what's the thickness of B? Is 15 millimeter. Okay, because B is just right below the dash line. So the thickness is 15 millimeter. Sorry, it's 30 millimeter. Sorry, 30 millimeter. 30 millimeter. Okay, so we have to everything together. So we have the T. Okay, so what's our answer? Our final answer. Our tau at B is equal to V is 19.5 kilonewton. Okay, and what's our Q at B? QB is 2.025 times 10 to the power minus 4. Okay, what's moment of inertia here? Don't forget your moment of inertia calculate is 2.7 times 10 to the power minus 5. And what is your thickness is 30 times 10 to the power minus 3 m. So after your all calculation, the answer is 4.875 megapascal. Okay, mega, big capital M means 10 to the power 6. Don't forget it. Okay, so this is the shear stress at this point B. Okay, and its maximum shear stress in this beam is 4.875 megapascal. Okay, so this glue has to provide maximum. I have to provide 4.875 megapascal shear stress to prevent the sliding of these two parts. Okay, so that's a very typical the shear stress calculation in beam. Okay, it's because you have to calculate the moment of inertia, also have to calculate Q. So that's really takes lots of time. So you have to get used to it. Yeah, that's very because I think you haven't done this calculation before. Okay, so good luck. Okay, good luck to you. Okay, see you in the next video. Bye bye.